Often in mathematics, we're very interested in the properties of functions. So what does a function do throughout, like globally, throughout the whole domain and range, and what does it do at a specific point? And that's a big part of calculus, especially with infinities. And what I mean by that is this is a really basic example. This is y equals x squared, or f of x equals x squared. If I wanted to know the behavior of this function, as our x as our input, we input smaller and smaller and smaller values. What happens to our output? That's really easy. We know as x gets smaller and smaller and smaller towards negative infinity, our y, our output, will go up and up and up. For example, we'll start with negative 100 squared, and then, negative 1,000 squared. And as we go to negative infinity, our output is going to be larger and larger. And this is a really basic example, but often it is not clear. And calculus, the first thing that we will talk about, studies the behavior of functions locally. So I'm going to give you an example. Let's take the function 1 over x, and I'm going to draw it really poorly once again, but I hope that's okay. Like that, right? So we have that asymptote right here. And I want to ask you a question. What does this function do? So as we make our input, as we input numbers closer and closer and closer to 0, 0.01, 0.000001, what happens to this function, 1 over x? Well, you might say, oh, that's easy. As we get closer and closer to 0, this gets closer and closer to infinity, right? 1 over 0.01 is what? That's like 1 over, that's like 100, right? Something like that. I don't know. And as we make this bottom smaller and smaller towards closer and closer to 0, this whole thing, this output, becomes closer to infinity. But wait, what about if we take it from the other side, right? So we make it closer and closer to 0, but like this, right? So instead of going to 0.01, then 0.0001, we start at negative 0.1, and then negative 0.01, negative 0.0001, and notice that we will approach negative infinity. So in other words, what we get closer to on this side is different than what we get closer to on this side. And in calculus, we have a very specific notation for this, and that is limit, right? So we say the limit as x approaches a of f of x equals L. What this means is we have a function, right? And it takes in a value x. As x gets closer and closer and closer and closer and closer and closer and closer to a, our output gets closer and closer and closer and closer to L. An example we gave before was as our input gets closer to negative infinity in x squared, our output gets closer to infinity. And what's interesting also there was when we had 1 over x, so as x went to 0 in 1 over x, the limit on the when we approached from the left was not the same as when we approached from the right. It was not the same. So here we say the limit does not exist. D, N, E. I'm going to give you another example that might be a bit more challenging. What if we wanted to see what happens as x approaches 1 in x squared minus 1 over x minus 1? Now there's a really cool trick, and I hope you guys will think it's cool. And here's what we do, right? So we take, right, you might, first of all, obviously you can't just plug in 1, okay? And if you wanted to, you could plug in values that are really, really close to 1, but that's no fun. Here's what we'll do. Let's factorize the top as x minus 1 times x plus 1 over x minus 1. And know that what we're doing is we're making x closer and closer to 1. So x won't ever be 1, right? X is just going to be infinitely close to 1. So in other words, we could cancel these out, right? And so we have the limit as, because it won't be 1, it'll be infinitely close to 1, but it won't be 1. The limit as x approaches 1 of x plus 1, right, is 2. As x gets closer and closer to 1 and x plus 1 gets closer and closer to 2. So in other words, as this gets closer and closer to 1, as x gets closer and closer to 1, our f of x gets closer and closer to 2. That's really cool. And what's interesting is what we just saw was we had a function that was undefined at some point, and we wanted to see, okay, well, if it was defined at some point, if it was defined at x equals 1, what would the value be? And in this case, it would be 2.